Tonight I'd like to show you how to use the mole as a conversion factor in some chemical calculations. Recall previously we defined 1 mole as equaling 6.022 times 10 to the 23rd particles. And when we're talking about particles in chemistry, we're usually talking about atoms in the case of elements, or ions in the case of charged particles, or in the case of compounds, we're talking about molecules. It doesn't matter what we're talking about. Whatever you have in a mole, you always have 6.022 times 10 to the 23rd particles or units. So we've written this as an equivalent statement, and I can, of course, generate 2 conversion factors. 1 mole of anything over 6.022 times 10 to the 23rd particles, or the 6.022 times 10 to the 23rd particles over 1 mole of the substance. So now I have 2 conversion factors that I can use to either solve for moles and cancel out particles, or solve for particles and cancel out the moles. Let's try a simple example. In this example, I want to go from 3.3 moles of gold atoms, 3.3 moles of gold to atoms of gold. So we're starting off with moles, and we want to get to atoms, our particles. And of course, we're going to use this relationship where 1 mole equals 6.022 times 10 to the 23rd and those conversion factors. So they're giving us that we have 3.3 moles of the gold, and we want to solve for atoms of gold. So I'm going to use the conversion factor from the previous slide to cancel out moles and solve for atoms of gold. So 6.022 times 10 to the 23rd atoms of gold for every 1 mole of our elemental gold. So moles cancel out. And when I did the math on this problem, I got to 2 significant figures: 2.0 times 10 to the 24th atoms of gold using dimensional analysis. We can also go the opposite way, where we start with atoms and end up in moles. For example, I want to convert 1.67 times 10 to the 28th silver atoms, elemental symbol Ag, to moles of silver. So in this case, I'll be starting with atoms, and I'll be going to the moles. I'm still using this relationship we generated previously. 1 mole equals 6.022 times 10 to the 23rd atoms. And it's atoms again because we're talking about elements. So using the starting point of atoms, 1.67 times 10 to the 28th silver atoms, I'm going to multiply it by a conversion factor that has moles in the numerator, so 1 mole of silver over the 6.022 times 10 to the 23rd silver atoms. That will cancel out atoms of silver and of course leave us in moles. And after dividing 1.67 times 10 to the 28th by Avogadro's number, 6.022 times 10 to the 23rd, I got 27,731 moles of our silver. And rounding that to 2 sig figs, I get 27,700 moles. 2 sig figs. So that's using Avogadro's relationship, 1 mole equals 6.022 times 10 to the 23rd atoms, to go back and forth between moles and atoms in those 2 previous examples. The other definition of the mole that we talked about is molar mass. We know that 1 mole of any substance will equal its gram mass of that substance. For example, when you look at the periodic table, you see that carbon has an atomic mass of 12.01 atomic mass units. We can now look at that in terms of units of grams per mole. So carbon weighs 12.01 grams for every mole of carbon atoms that you have. And this is a ratio so that I can generate now two conversion factors. The molar mass as we typically write it, grams over moles, or I can flip it so that the moles are now in the numerator and the grams of the carbon in the denominator. This is a very useful conversion factor because it allows us to go from grams of the substance into moles of the substance, or from moles of the substance back into grams, using this molar mass as a conversion factor. For example, perhaps I want to convert 3.3 moles of carbon to grams of carbon. In this case, I know that from the periodic table that carbon weighs 12.01 grams for every 1 mole of carbon. I'm starting off with 3.3 moles of carbon, and I'm going to use my conversion factor as written with the grams in the numerator, 12.01 grams of carbon in the numerator, and the 1 mole of carbon in the denominator. That will cancel out moles of carbon and leave me in grams of carbon. And rounding this to 2 sig figs, I get roughly 40 grams of carbon. Note I put the decimal in there to show that that trailing zero is in fact significant. So I can use the molar mass, the 12.01 grams per 1 mole of carbon, as a conversion factor to convert from moles of the substance to grams of the substance. How about this example where we're given 47.1 grams of carbon and I want to convert to moles of carbon. So again, we want to use this relationship where moles are the center of our universe and we convert back into grams using the molar mass as a conversion factor. So in this case, we're starting with 47.1 grams of carbon. From the periodic table, I know that 1 mole of carbon equals 12.01 grams of carbon. So there's the molar mass as written. I'm going to flip it so that the moles are in the numerator of my conversion factor. So 1 mole of carbon over 12.01 grams of carbon. And this way, using dimensional analysis, when I multiply by that conversion factor, the grams of carbon cancel, and I am solving for what the problem asks for, moles of carbon. And after I plug this into my calculator to 3 significant figures, I got 3.92 moles of carbon. Now, in each of these problems, you can ask yourself whether these answers are correct. If you have exactly 1 mole of carbon, it should weigh 12.01 grams. In this case, we don't have 12.01 grams. We have 47.1 grams, which is significantly larger than 1 mole. So the number of moles should go up every time you have a mass that is greater than the molar mass given in the problem. In the previous example, if we look at this example again, where we had the 3.3 moles of carbon and converted it to grams of carbon, if we have 3.3 moles of carbon, that is significantly more than 1 mole of carbon. 1 mole of carbon will always weigh 12.01 grams. So starting out with the moles, we multiplied and we got 40 grams of carbon. So you can look at your answers and determine whether or not they make sense as to your knowledge of the mole. Now let's try a little bit harder example here. A graphite pencil, and graphite is nothing more than an allotrope of carbon, contains 55 milligrams of carbon. I want to know how many atoms of carbon are in the pencil. So this sounds like a very tricky type of problem, but it isn't. In all chemical calculations, we have to go through the mole. So the mole is the center for all of our calculations. And the first thing we see in chemistry is a lot of times we like to get into grams of our substance. So we can go from grams of a substance, and I'm just going to say substance A, to moles of substance A by using the molar mass. And we did that in the previous examples. Once we're in moles, we can then use the relationship that we generated with Avogadro's number to get into, in this case, atoms, because we're talking about an element here. So once I'm in moles, I can use the fact that 1 mole of anything contains 6.022 times 10 to the 23rd particles, in this case, atoms. So if we look at this problem, we're going to be starting off with milligrams. We'll convert that into grams. We'll use the molar mass of carbon, the 12.01 grams of carbon per 1 mole of carbon, to get into moles of carbon. Once I'm in moles of carbon, I'll use Avogadro's number to get into atoms. So this problem will look like this: 55 milligrams of carbon times our metric conversion factor, 1 gram over 1,000 milligrams. Resist the temptation to break this up into multiple problems. You'll just introduce a transcription error or a rounding error. Right now I'm in grams of carbon. Now I want to use the molar mass to get into moles, so I'm going to flip it. 1 mole of carbon from the periodic table is 12.01 grams of carbon. That cancels out grams of carbon. That gets me into moles of carbon. Now I want to get into atoms from moles, so I'm going to use Avogadro's relationship, the 6.022 times 10 to the 23rd atoms for every 1 mole of carbon. And that will cancel out moles of carbon. When I do the multiplication across the numerator, 55 times Avogadro's number, 6.022 times 10 to the 23rd, and then divide that by 1,000 times 12.01. To two significant figures, I get 2.8 times 10 to the 21 atoms of carbon. And that makes sense to me because we're starting with significantly less than 1 mole. If we had 1 mole of carbon, we should have 12.01 grams. We don't have 12.01 grams, we have 55 milligrams of carbon. So this is making sense to me. I hope you found these examples helpful, and I will have some more coming up shortly. Thank you.